तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In this lecture we will continue the design of traffic light controller, which was introduced in the last lecture. In the last lecture we specified the problem with all the requirements of the traffic light control. We drew the ASM, and now the next step, as we know, is to draw the ASM table and get the hardware implementation. And the ASM table can be drawn easily from ASM chart, which has been drawn as in the last lecture. And once you have the ASM table, as the mapping the hardware is easy. So in order to recapitulate what we did in terms of specifications, we will quickly go over the specifications of the traffic light controller. First, it is in reset state. So I will say this is sort of an algorithm, but not in the ASM form. Just to give you an example, give you a quick review as well as sort of a summary of the specifications. Reset state. First, the reset state, timer is started, and we go to the main red. Remember we discussed the lights as M1 and M2. So M1 green, M2 green, both the main road lights are green. Main turn right, that is the turning from the main road into side road. The right turn is red, and side turn, turning from side road into the main road, again right, is red. And then this will go on for the time if Tm T is equal to or greater than Tm and S1 or S2 is 2. That means after a specific time has elapsed in the main road, green, and also if there is a sensor, one of the two sensors S1 or S2 is activated, we will go to step 3, where we will retain our main 1 green, main 2 will become yellow, turn will be red, side will still be red. Yellow is a fixed time, after T yellow, that means when you have an yellow, when you enter the lights, you allow for a while for the traffic to slow down and stop. So, that is the time, yellow timing we call it Ty. After this, again M1 continues to be green, M2 will become red and MT will become green, turn signal will become green. Side road going from side to the main is still red, because we can only have one turn at a time, not the other turn. We cannot have both the turns at the same time because of the collision. And then we have a specific time interval for which the side street will be green or the turn signal will be green. So, that time we will call it side after Ts. After Ts, M1 continues to be green, M2 continues to be red, MT will become yellow, side street continues to be red. Now, we have an yellow period again. After Ty, if there is, since we have come to the turning because of S1 or S2, S1 or S2 being true, if S1 was true and S2 was not true, that means there is no requirement of traffic from the side road into the main road, then S2 will not be on. So, we do not have to spend time to give the green signal for turning from side road to main road, we can return to the main sequence. On the other hand, if S2 happens to be 1 and because of that we got into this, either because of that or because both S1 and S2 were on, both these two conditions, we would like to service the side road turning into the main road before we return to the main loop. So, that has to be tested here. After T yellow, if S2 is 0, then we will go back to this step. On the other hand, else which means after Ty, if S2 is not 0, that means if S2 is 1, we will have to go and stop the main road traffic, both sides continue to stop it and then allow for the turning from the side to the main. So, in this case what we are specifically assumed was the main road from left to right will be green when you allow the turning from main road into side road, whereas the same green from main road from left to right will not be green when you allow the turn from the side road to the main road. That means the main road should be stopped, the traffic in main road should be stopped in both directions now. That means I need to go for M1Y, M2 will be continues to be red, M2R again, I am sorry, MTR, M2R, MTR, MTR, side red still. After Ty, it becomes M1 red, M2 red, MT red, S green. That means both sides of the main road traffic as well as the turning signal from the main to side, they are all red, side street is green, so that it is allowed to go. And again you have after TS the side street period for which it is green. We will go back, continue to be M1R, M2R, MTR, SY, side street become yellow, after Ty we can restore the original condition of main green, M1 green, M2 green, M2 green, empty red in SR. That will be step 2 again. Go to here. Actually, I should have written here go to 2. I am sorry. Go to 2. Go to 2. Step 2 is what? Step 1 is only reset state, just to start the timer so that the sequence starts. So, the actual most of the time the traffic, if there is no, assuming there is no sensors activated any time S1 and S2 are both zeros, the traffic will continue to be the system will continue to be in state 2, which is M1G, M2G, MTR, SR. So, it should be really go to 2. Here also it should go to 2. This, as I said, is a quick summary, and each stage I have not shown something. Each stage we are supposed to start the timer. So, here I should say do this. When you go from 2 to 3, we start the timer. Go to 3 to 4, start the timer. So, everywhere you have to start timer. In this process of going from each state to the next state, the timer should be started. That I am not showing independently here. So, what I should really say, if t is greater than Tm and S1 is true, start timer and go to M1G, like that I should say. Similarly, I say M1G, M2Y, MTR, SR, and after Ty, etc., start timer. So, start timer should be put in each stage, as I did put here. So, that is assumed. So, this is just to recapitulate the ASM, because it looks a little complex. And now with this background, I want you to look at the table. This is the ASM table. So, huge table.
Sir, if S1 is not 1 in the second case, then we are unnecessarily turning the signals to the right turn. Yes, sir.
See, yes, that is a good question. The question is, since we are testing for S2 before proceeding or returning back to 2, why can't we do a similar thing for S1? That is the question. That means I should every time check S1 and S2 and take appropriate action. Yes, it is done. See, I wanted to introduce some specifications and how the specifications are properly met in your ASM and your hardware. This, of course, there are design flaws. Design flaw is different from the circuit flaw. That means you may not think of a case, and as long as it works for the specifications you give 100% perfectly, it is okay. I deliberately chose this because already the ASM and the number of states, the number of the ASM became first example, a very simple example. This example is sort of an order of magnitude more complex, more than an order of magnitude complex from the first example. I can do that. First I can check S1, like we did RA RB case in the first example. We did request for bus A, request for by system A, request by system B for the bus. So, if RA RB was tested and then some sort of priority, here also you can do the same thing. S1 and S2 will be tested in sequence, S1 given priority, then S2, we can do that. But then each of these S1 S2 testing has to be done after every change of signal. That means the ASM becomes more complex, more number of states will be introduced, but if that is what you want, you can do it. This example very clearly defines every time either of these two signals, I am always going to give a benefit for the main road to side road traffic. There is a reasonable assumption some of the traffic will go from main road to side road. So, this is an assumption in the problem, inherent assumption in the problem specification. I am not making this assumption after the problem is given to me. I am assuming this is one of the specifications that main road will always be given a chance, whereas side road, in fact easier for me would have been without going through this test here. In fact, I do not even have to have a sensor. There are several possibilities. Suppose I do not have a sensor at all, what is wrong? I allow for the main street to be green for a while, after that time I go the side from main to side, allow it for a time while, and after that I from side to main for a while, and then go back to the original. That is one simple way of doing it. Number of states will be reduced. One modification will be one of those can be sensors, depending on which is less likely to occur. Sensor will be put in a place where it is less likely to occur. Third is put sensors in both and then verify each sensor every time. That will become more complex. I sort of took an intermediate path, a mid path. Wanted to make the problem reasonably complex, number one. Number two, I want to make it slightly different from the routine problems that you will find in any traffic light control example, because traffic light controller has been a problem of choice with many authors. You will find the main road side road traffic problem in almost every book in digital design, from gate level to ASM to FPGA to ASIC to microprocessor based. So, of course, you will understand it when you read it, but if you give a specific slightly different specification and explain it, if you understand that, then I am confident that you have understood the concept of design. That is the example. Does it answer your question? Okay. Now, with this you go to this table. You are not expected to memorize this table, it is a huge table as you can see here. There are states here S0 to S7, each state we have taken a binary assignment, it is called natural binary assignment, run without any specific guideline for states. S0 corresponds 0 0 0, S1 0 0 1, S7 1 1 1, 8 states, 3 variables, we will call them ABC. The conditions are very simple: timer yellow not completed, completed, timer site sheet not completed, completed, timer main completed, not completed, sensor here S1 S2 both are marked in this first stage, whereas only S2 is monitored in the second stage. Based on that they go to the next state. We drew this ASM, you can correlate this with the ASM that you drew, and from this state the condition to the next state and what is the output in each of these states. For example, you can see in state 1, in state let us say in state 1, or make it a simpler state, state 2 which is 0 1 0, all we are looking at is yellow. This is main 2 yellow, M2 yellow. M2 yellow we are allowing for the yellow time to be over before we turn it off to red, so that we can allow the side traffic, main traffic to side road. So that is the condition here. If it is not there, you continue to be in this state. After that you go to the next state, and so the lights are correspondingly marked here. No start timer. The start timer will come only when you want to go to the next state. Whenever you want to go to the next state, you start the timer. So ST stands for start timer. These are output signals. These signals are the light signals corresponding to the lights. M1G, M2G, MTR. So main M1 green, M2 green, main turn red, side red, M2 yellow, M2 red, M turn green, M turn yellow, M1 yellow, M1R, side green, side yellow. The reason it is written in a random order, not in a, would have normally like to see M1G, M1 yellow, M1R, M2G, M2 yellow, M2R. That is one way of writing. This way has been written in the order in which they appear in the ISM chart. The order in which these outputs appear in the ISM, we have put it in that order. So as corresponding to the state of 0 1 0, you are waiting for the yellow time to be over. As long as the yellow time is not over, you continue in the same state, keeping the main 1 green, main 2 main empty red, turning red, side red, M2 is in yellow state, all others are zeros. When the turn occurs, the time is over, everything is same except that we start the timer. So the same set of outputs with starter 1, start timer 1, and then it goes to next state 0 1 1, wherein now the yellow has completely turned, it has become now red, and the turn has become green. So it will become main 1 green, main 2 main 2 red, main turn green. So main turn is green, main 2 is red, main 1 is green, all others are zeros. This is how you write the table. So once you have, this is purposely has been chosen the problem with so many things, so that you know you can handle systems. The system complexity does not change this design complexity. Design is the same, procedure is same. More and more number of variables, more and more number of conditions, the ASM becomes larger, number of inputs and outputs become large, so you have to handle them carefully. You have to exercise extreme care in drawing it, and because once you draw this, this is going to be implemented in hardware. This is all right here, and then if you want to do a Verilog coding, the whole thing will be written in a Verilog, and then you have to synthesize it and get into an FPGA or whatever it is. So you have to be extremely careful. If you make a mistake, you have to redo everything all over again, and then you have to recompile and do everything again and again until you are satisfied. So I am not going to explain this table. I already told you how to get this table, and the hardware blocks can be, these are ABC, present state and next state. We have already seen it, how to do a multiplexer based solution for this. So we have 8 to 1 multiplexers with 3 selector variables ABC. So there are 3 multiplexers required here, one for A, one for B, one for C. So there is a multiplexer for A, the multiplexer for B, multiplexer for C. We call it A plus, B plus and C plus to indicate they are next state variables, and what state they are in is given by this inputs ABC. ABC inputs are given to selector 2, selector 1, selector 0. In 8 to 1 multiplexer will have 3 selectors S2, S1, S0, to which we are applying the present state ABC. So present state ABC is given, next state variable A plus, present state ABC is given, not shown here. Already the drawings are too many and cluttered, and we do not want to increase the complexity of the drawing. So ABC are the inputs, and then B plus is the output, ABC is the input and C plus is the output, and what to give to each of these inputs depend on this table. For example, when you are in state S0, the condition under which the next state is 0. So for the first input of the first multiplexer corresponding to A, you give 0 as the input, so I0. So wherever there is 0, we have combined them, I0, I1, I2 are all zeros, because the first 3 entries are all zeros. I1 corresponds to this first state, I2 corresponds to second state, I3 corresponds to third state. For all these states, the next state variable of A is 0. So I1 has to be 0, I0 has to be 0, I1 has to be 0, I2 has to be 0. So all of them have been combined again to reduce the drawing. So like that you can draw the inputs, write the input conditions for each of these inputs I0 to I7 for each of the multiplexers A, B and C, and then the outputs can also be given by multiplexer. I will give you one example, the rest you can see. For example, we will see how to get the start as an output. I will just get the, so these are the inputs, I mean the next state variables, A plus, B plus and C plus. Each one is an 8 to 1 multiplexer with 3 selector variables S2, S1, S2 connected to A, B, C. 8 inputs I0 to I7 connected to corresponding conditions based on the table. Already explained to you 1 or 2 here, that is how it is done. The rest of the things, all others are for outputs. Before I go to the output, I will tell you how to get the output by taking one example. Let us take start signal as the example, rest you can follow based on this. So again there are only 8 states, hardware implementation for ST stands for start timer. 8 inputs, 1 output, mux, A, B, C, present state variables, 3 selectors. This is the start output. F is the output of the multiplexer, that is the output start. 8 inputs, 1, 2, 3, 4, 6, 7, 8, I0, I1, I2, I3, I4, 5, I6, I7. What are the conditions under which the start signal is 1? That is all we have to map in this multiplexer. In this multiplexer we have to put this by looking at the conditions under which start is 1. Start is 1 for the present state 0 0 0. So if we are in present state 0 0 0, start is a 1. Start is a 1 in S1 provided the condition Tm S1 or S2 is valid. So correspond I1 I will have to put Tm S1 or S2. That means after the elapse of the term time Tm, the main road green time, and if one of the sensors is true, then start timer will be initiated when you are in state 1. This is how you map it. So we have taken care of this. Simply looking at the table and writing. For everything else, it is the condition. From S2, the output will be 1 if start will be timer 1 if Ty is 1. So it is Ty. In S3 it will be 1 if it is Ts. Usually the start timer is usually after the elapse of the time. So after elapse of Ti, after the elapse of Ts. In this case it is one of these two conditions, Ty S2 or Ty S2 bar. You can combine them and write Ty because S2 or S2 bar get cancelled because S2 plus S2 bar is 1. So it is again Ty. When you are in S4, when you are in S5 again it is Ty, almost it is Ty. S6 it is Ts, S7 when it is Ty. So the timer outputs, because we had a timer, remember we had a timer in the functional block. The timer started with a start timer signal, and then we had the clock, and then we had these conditions Tm, Ty, Ts. It is a functional unit. So these things are available here, and depending on which state you are in, after this again yes, thank you. So depending on which state you are in, a corresponding input will be given so that the start timer will be, the timer will get started again. That means you are resetting the timer again and again. The output and input are same, which means what? The start timer, and then when you put it, it resets and gets started again, resets and gets started again. This is an example of one of the outputs. So all other outputs, there are 13 of them I guess, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There are 13 outputs, one is there. All other 12 outputs correspond to 4 lights. There are only 4 lights, is it not? Main 1, main 2, main turn, side. 4 lights, each light has a green, yellow, red. So 4 times 3, 12 lights. Start time is the 13 signal I already shown here. The 12 lights are very easily written here. M1G, whenever the input is in the state 1, 2, I1, I2, I3, I4, M1G is on. Rest of the inputs are 0. So all inputs not shown are zeros. All inputs not shown are zeros. Similarly for MT red, I1, I2, I5 to I7. I1 to I5, 1 for SR. So like that you can write it. Some of them need not, you don't even have to have multiplexers. These are 8 to 1 multiplexers, 8 inputs, 1 output, 3 selectors. But when the number of outputs is not large, you don't need to use a multiplexer, you can use a simple gate. For example, M2G is A bar, B bar, C, only one case. So put that here. M1R is only AB, so put a 2 input gate. So if you do not want these gates here, you can also replace them by multiplexers, because we know how to do all that. So that means we have now, in summary, we have taken an example. Yes? State flip-flops are assumed. Yeah, multiplexer based solutions, state flip-flops. The question is, I have not shown the state flip-flops. All of us know that the multiplexer based system, there will be state flip-flops. What is meant is here, I will now remove this table. you don't need it. I am not drawing the full block diagram. Now that there is a question about where do you include the state flip flops, it is like this. There are only 3 flip flops. I think this is something which we already described in detail in previous state graph technique as well as the ASM technique using multiplexers. Each variable will have a flip flop, is a D flip flop, Q is connected. So this will be my A plus, if you want to call it that. Actually A or A plus is the same, because the present state, next state becomes present state, and then the complement of that. Okay, want to be having A because A plus is the input, whatever. So this is the input corresponding to dA, which is also called A plus. B plus or dB. I think we have done all these things again and again. See, we can't be going on doing these things in every problem. So, assumed architecture. So, each of these is given by a multiplexer, which is 8 to 1. And this is connected here, and ABC are the inputs, selectors. I0 to I7 will be connected as shown in this diagram. So, the 8 inputs of these will be connected according to this for A, for B, for C, and then we have extra circuitry for output functions, either using multiplexers, using it. So, as I said, to summarize, we have taken an example. Yeah, good. Clock, yes, of course. Without clock, it will not work. Thanks. So we have. So we have clock here and we have all of these things here. So given a problem, understand its specifications, systematic step by step procedure, call it algorithm if you want, and then write a ASM chart, identify the signals input and output for the controller, get the ASM table, get the implementation using flip flops or multiplexer or whatever, and then go to the output also using flip flops, using multiplexers or gates or whatever, and do the same thing for the outputs either multiplexers or gates, and then you have the whole problem, connect them together like this. This architecture is common. I do not want to be doing this repeatedly, because somebody asked here in this class. I again did this because we have done it several times before. We did it in the case of state graph, we did it in the case of the first example of the multiplexer, to avoid repetition, and also because by now you are familiar with this architecture. Output of the multiplexer drives the flip flops, that is it. You have to assume all this. This architecture is standard. The size of the multiplexer depends on the number of states. Up to 8 states, multiplexer will be 8 to 1. Up to 4 states, multiplexer will be 4 to 1. Up to 16 states, multiplexer will be 16 to 1, like that. And then the inputs of the multiplexer, the only thing which are different. Inputs of the multiplexers will be the only thing different from problem to problem to problem. To that extent, it is a very simple design. It is all fixed except to find out this. That will be written directly from the ASM table. That is what I am trying to say. Of course, you want to have a ROM based solution for this. Yes, it is possible. What will be the size of the ROM that will require? We have 8 states. Supposing you have a ROM based solution. What do you mean by ROM based solution? The ROM keeps everything and drives the flip flops. let us call these flip flops a register, 3-bit clock, which is common to all the 3. Okay. Now, the outputs of this, these are A plus, B plus, C plus, D, 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 Q, Q, Q. Clock is common to all the 3 flip flops. So, this will be my A, B and C. In addition, I should give all the inputs and get all the outputs. There are 13 outputs, I said. So, this will be 13 in outputs, starting with ST, M1, G, M1, yellow, etc., M1 red, all these outputs. How many inputs will be there here? The input will be the start timer, no, input will be Tm, T yellow, Tm, T yellow and T side. These are the 3 inputs. Is there any other input here? Ts, Ty, Tm, S1, S2. These are the inputs. Are we leaving out anything? No. These are the only inputs to this. So, the size of this ROM would be 5 plus 3, 8 inputs, 13 plus 3, 16 outputs. So, it is size is 2 power 8 into 16, or it is 256 into 2, or 256 into 2 power 8 is 256, right, into 2. So, it will be 256 into 16 bits, or it is 512 bytes. But we have a 512 bytes ROM or byte organized ROM, 512 words. I can realize this. All we need is, in addition, 3 flip flops. This is a ROM based solution. It is very simple. My ASM chart will be expanded. In ASM chart now we had only rows corresponding to a condition. There are 8 states, 0, 0, 0 to 1, 1, 1. So, each of these states, if you expand, there will be 256, because how many? Each of these, there will be, each row on each condition. So, the size of the truth table would be, because of 256, there are 3 inputs and 5 conditions. We will have to write a row for each of these states and each of the conditions, which means my ROM truth table will be ROM table, as it is called. We will have 256 rows, each row having 13. Expand expand ASM table to a ROM table. That is all you have to do. ROM table will have 256 entries, A, B, C, S1, S2, Tm, Ty, Ts, 8 inputs. That means (256 rows), and there will be, and all these 16 columns. That is how we got this number 256 into 16. 256 into 16 we got because there are 256 rows and 16 columns. But the ASM table has been expanded. For example, 0, 0, 0 state gave an output of whatever is the condition, 0, 0, 0 state goes to the next state 0, 0, 1. If you remember the ASM, I am just telling from memory, please refer back to your notes. In ABC there is no condition, you go to, in the S0 state there is no condition, you always go to 0 0 1, and what is the output in the state? ST. ST is the output in the state. Start timer, and the lights can be main lights, is it not? So irrespective of the condition, and this will be M2G, M1G, rest are all zeros. Or if you want to write red and all that, so I am not going to fill this. This one like example. Now this XXX will not hold in a ROM table. In the ASM table I can have an XXX because I am only looking at the conditions for next transition. Now this XXX, 5 X's have to be expanded into 32 rows, 5 inputs, so I will have to start with 0 0 0 0, 0 0 0 0 1, so for 32 rows. All of them having the same output. This block will have same output. So you have to store in 32 locations, first 32 locations of the ROM, the same word, 16-bit word. Like that you go to the second, and you have to exhaust all the 8 states. So that is how you get the ROM table. So all you need to do is to get an expanded ROM table and program the ROM for this application. Of course you do not give it in this form. In a ROM table, you know, you do it in hexadecimal form. ROM table is not written in binary because it is so huge to write. ASM table or state table we write in binary, or truth table we write in binary. ROM table is generally written in hexadecimal form, so we can compress the number of the size of the table. So this will be written as 0 0 hexadecimal, this is 0 1, this is 0 2, like that. So the hexadecimal ROM table will look like location or address. When you say ROM, it is only address, no? And content. Of each address, what is the content? So 0 0, 0 1, 1 0 2, 0 F, 1 0, 256. So it will be FF. And each of these rows, what do you have to put? So in the first table, for example, something like 0. This will be first is 2, no? First is 3 and something, I do not know what it is. I have not written the table in full. And this 3x will continue. This is not x, do not put x in your table. I am just writing x because I have not fully written all the rows. In fact, I can do it and make sure that the way in which it is appearing, it will become ST M2R M1G, M2G, MTG, SG, and then we will repeat it for yellow and then repeat for red. If we take that, what will be the condition here? Main will be green, this will be green, this will be 0, this will be 0. And then the yellow case it will be 0 0 0 0, red case it will be 0 0 1 1. So the first word will be 0 0 1 1 1 1. So this will be first 8 1 2 3 4 5 6 7 8. It is C. 3C 3C3, that is 3C 0 3 3C 0 3 3C 0 3, 32 entries like this. This is how you do it. And then you can go to the next step and have a programmable array logic. We will not go over all of those again because I know the difference. Already we have discussed the difference between Pil approach and the ROM approach. Again, ROM approach, Pil will have a Pil table, which is a simplified form of a ROM table, because we will redundant entries where there is no activity. Redundant entries where there is no activity will be removed. Pil will have fewer rows or fewer product terms. And the output, another advantage is the registers are included in the Pil. I can have a Pil or a PLA, usually Pil, in which register is part of the device. So, in single device, all I need is, I need to look for a device which 5 plus 3, 8 inputs. So, the Pil approach. We have seen the design of Pil earlier, so I am not going to spend time on it. So, Pil based design, eight inputs, 16 outputs, out of which at least 3 should be registered outputs. Three should be registered outputs, 3 registers are required. Of course, there should be a clock input, and we will have to have sufficient. I am not going to go into the counting now. So, sufficient number of product terms, sufficient number of AND gates for each output, to fit the design. We will say it and leave it here. So, there are standard things. Anyway, we are not going to design your AND gates. We are going to look through the library of a manufacturer and then decide the appropriate device for this purpose. We already seen the Pil based design our earlier examples. So, that will be used here. So, in summary, then we have now a elegant method of drawing a chart, drawing an algorithm based on a specification, identifying the functional blocks, identifying the signal, drawing the ASM, getting the ASM table, implement in whatever form you want. Gate form, you want to write corner maps and simplify the number of gates, or multiplexer based form, or ROM based, or Pil based. With this, we will stop here at today's lecture, and we will see one more example of a slightly different nature in the next lecture. Thank you.